So the pre-lunchtime talk will be given by Rene.
Okay. Well, thank you for giving me the opportunity to talk. I want to come from a slightly different angle than most speakers here. I want to come more from, not from an fMRI or an MRI angle, but more from an electrophysiology and EEG angle. So I started working in neuroscience by measuring simultaneous EEG and fMRI. And the question I always ask myself is, okay, we have these EEG features, and mainly EEG oscillations. How do they relate to the bolt signal? Where do they relate to the bolt signal? And from there on, I got involved in doing laminar fMRI, and in the end, the latest experiment I've been doing, I've been looking at how feature-specific laminar fMRI relates to specific EEG features. So that's going to be the topic of this talk. As I said, I want to start with electrophysiology, and a very short, way too short introduction. And I mainly want to focus on oscillations, and you can want to look at some work done in, I think, monkeys more than a decade ago. And what was found was when monkeys perform an attention demanding task is that you get increases in both in synchrony in both low frequencies and high frequencies. But if you look at the depth of the electrodes where you can measure the maximal signal, what you can see is that low frequencies up to 10 to 20 hertz are mainly found in the deep layers. Well, high frequencies, so gamma band frequency, around 40 to 80 hertz is mainly found in superficial layers. And this has been replicated later on, and that the low frequency seem to be more related to deep layers, while higher frequencies, and specifically gamma band, seem to be more found or recorded from superficial layers. And this has, frequencies have also been related to differences in how they relate to feed-forward and feedback processing. So the idea would be that the high frequencies, so the gamma band, is more related to a bottom-up feed-forward flow of information, for instance, from V1 to V2 to V4, while the low frequencies in the alpha and beta range are more related to the opposite direction, so going from higher order regions to lower order regions. So it's more or less depicted here. So if we here have a very simplified canonical way of how we think about how laminar connections in the brain work. And the idea would be that information comes into the granular layer and is fed forward from the supragranular layer to layer 4 in a higher order region, region B, and that this connection would be mainly related to gamma band oscillations that, well, feedback related oscillations that originate in the deep layers of the higher order region would feed back to both the infragranular and the supragranular layer, well, sparing mainly the middle layer. So this is the canonical model that is proposed here. As I said, I'm mainly interested in how to EEG features related to the bolt signal, and in previous research I've actually looked into it more specifically more at a non-laminar level. I used a visual attention demanding task that gives strong activations in visual cortex, and what I did is I correlated every single frequency in the EEG, and so this is the EEG response to this visual stimulation with the fMRI. As you can see, this task will give you decreases around 10 and 20 hertz in the beta bands, in the alpha and beta bands, an increase in the gamma band 60 to 80 hertz. And if you look at the EEG bolt relationship, we can find correlations deviating from zero, specifically at these frequencies, with negative correlations for the alpha and beta bands, and positive correlations to the, for the gamma bands. So as I explained to you before, we have linked these different frequencies to different cortical layers. So when David was developing his laminar work, I was always interested to see, can we see whether these frequencies correlate with specific layers in the cortex. And that's an experiment I did together with Peter Koopmans when he was here at, who was previously here at the Hahn Institute. And what we did is we did a variation of the experiment I did before. So here subjects had to move, look in the inward movement grating, and there could be a speed change happening in this grating when they had to, and if that happened, they had to press a button. The likelihood of this speed change was skewed, and when it was skewed, it was 67% likely to happen, and when it was skewed that it wasn't happen, it would certainly not happen. And this gives us an attention contrast that we will later also use. And what we did is we used an interleave sequence where we had one trial in between every 3 volumes. And simultaneously, we measured laminar resolved bolt signal at V1, V2, and V3. It's should say 0.75 millimeter isotropic, and we did it actually at 7 Tesla. At 3 Tesla in Nijmegen. So, these are the quick basic results of this experiment. So again, what we find is we find a negative, a decrease in alpha band and beta band, and an increase in gamma band, just like in our previous experiments. But also attention modulation shows now an effect in these exact same frequency bands. And this is a quite strong effect, and we find a decrease with attention in alpha and beta band, and an increase in gamma bands. And we will later use this to correlate that with the same effects in laminar fMRI. This shows the topography nicely over visual cortex, where you would expect it. And here we've illustrated V1, V2, V3 in one specific voxel, in one specific subject. And the dots indicate the voxels that we selected that were maximally responsive to the task. Here we have the fMRI attention effect, and what we can see here is that there's no specific laminar profile in there. So basically you get an attention effect across all layers for all 3 responses, maybe with the exception of V3. I should say here that the boundary CSF gray matter is here on the left, and the boundary gray white matter is here on the right. So the question is, how do you combine this EEG response with this fMRI results? There's 2 ways to integrate EEG and fMRI, and the first one is to use the variation in the EEG response that you have over trials and correlate that with the variation you have in the fMRI response over trials. So if you would have an EEG or a variable here, then here every single point would be a trial or a time point, and you would have a bold variable, let's say a bold amplitude response, and you can just basically correlate the 2. In practice, what I do is I pick my EEG feature, let's say this is alpha or gamma band power, and I quantify it for every single trial. So if the black would be the average, then I just take the amplitude for every single trial, and basically implement that as a parametric modulation in my fMRI analysis. So I construct a parametric modulation based on these EEG responses, and with that I can analyze my fMRI data. So if we now take this spectrum from our task that we have, is what I did is I didn't just make one model with one regressor. What I did is I constructed a specific regressor for every single frequency. And so I have for every single frequency a regressor, which I can use in a separate model for every single frequency. And what this does is it gives me a spectrum of how the bold relates to the EEG signal. And that's depicted here. And since we also have estimated cortical depth width in this experiment, this will result in a 2D image. And should be read as follows. On the x-axis, we have frequency, split up in low frequencies and high frequencies with a different spectral resolution. And the y-axis, we have interpolated 21 points across the cortical width of the cortex, with the boundary white matter, gray matter at the bottom, and boundary gray CSF at the top. And the colors indicate the strength of the correlation or the strength of the second level test that we did on this data. And what we found here is that we find basically a correlation with the alpha band across all cortical depths. For the gamma band, what we find is we find correlations that are only there for the middle to superficial layer activity. And this makes some sense if you think about the hypothesis we had about both alpha and beta bands. So this is for V1, V2, V3 combined, and it basically replicates for the separate regions as well. What is most strongly actually there in V2 and V3. So this is one way to integrate it. Another way what you can do is you can actually quantify per subject the attention effects in both fMRI and also in the last second of the EEG here. And if you do that, you can correlate these attention effects over subjects. And in this case, we have 30 subjects. And you can see how the attention effects in the two modalities correlate with each other. And this will give you a similar plot as I've shown you just before. So again, here, now this is the correlation of the attention effects. Again, frequencies on the x-axis, cortical depth on the y-axis, just as is explained to you. But this gives a slightly different picture now. What happens is that for alpha, it seems to be, in this case, mainly correlated with only the superficial layers. This will indicate that probably we are actually capturing two alpha processes, and only one is related to the attention effect in alpha. But we also now find the beta effect popping up, which is mainly located in deep layers. And this is a nice contrast with alpha because they typically go together. So whenever alpha goes down, beta goes down. But you can here clearly see that it's in our task, it's separate processes in both superficial and deep layers. And in line with our previous result, we find middle to superficial layer correlations with the gamma bands. And especially for V2 and V3. For V1, it seems to be a bit more spread out across all layers. But for V2 and V3, it's mainly in middle to superficial layers. So this is still all non-feature specific. And the next step what we did is we wanted to look at, okay, alpha and beta and gamma, they've been related to feature specific feed forward and feedback processes according to some models, especially gamma band has been related to that. And together with two people, Tommy Clauster and Mathilde Bonfont, we conducted an experiment and where we wanted to look at feature-specific laminar bolts and how they relate to these processes. And the work that I'm going to present here, I go to the correlation with EEG, with fMRI. First want to show you the EEG response we have here. So this is the average response over subjects. And should say we have roughly 50 subjects for this experiment. And what we did is we did source analysis on our EEG to denoise our EEG data, and we placed one dipole in the left hemisphere and one in the right hemisphere and used a beamformer technique to denoise it. And what we have here is the low frequency and the high frequency responses, average responses in the left and right hemisphere. And what we see is that we can clearly have a decrease in alpha bands and an increase in gamma bands relative to the stimulus. And it's strongest in the earliest part of the response and the early part of the trial. And that's why we also want to focus on the early part of the trial. So we want to focus on the trial, part of the trial that's typically before the subjects give a response in the oddball trials. So that's what the correlations I'm going to show you pertain to. And we also pre-selected, we also focus mainly on the alpha and the gamma band. So we have a bit of a beta band, but it wasn't very, it's good. I got 5 minutes, that should be enough. We don't have much of a beta band response in this task. It was a bit disappointing, but that's why we decided to mainly go for the alpha and the beta, alpha and the gamma responses here. So first, the gamma band response. So what we have here is basically the strength of the relationship between frequency and the bolt signal for deep, middle, and superficial layers, and red, blue, and green. And it's hard to tell. And actually, for the presented stimulus, there wasn't directly on its own a significant correlation for the gamma band. So it seems to be positively correlated in general, which is what you would expect. But in the selection I'm presenting here, we didn't find a strong positive correlation. And same for not presented, it seems actually to go negative, but we don't find a strong correlation here. But if you actually compute the difference between these spectra, what you do find is actually a peak at 50 to, let's say, 55 to 65 hertz, where we do find a correlation with the bolt signal that is stronger for the presented versus the non-presented stimulus. So it seems to be that the difference between the two conditions does give you a significant result. And if you look at the frequency range, it's 55 to 65 hertz. And if you go back to EEG, that is exactly where we find the main response for our gamma band. So in that sense, it looks like that we are sensitive to something real here. So this is basically the significance for all different layers. But if we now, for this significant part, zoom in at the deep, middle, and superficial layers, and we average across this frequency range, what we find is we find a monotonic increase from deep to middle to superficial, which is in line with gamma being more related to superficial. And I think if we test for this monotonic increase is actually significant over subjects. It's not a big effect, I must admit, but if we test for it, this does come out of the the complicated test that we just came up for this, and there seems to be a monotonic increase in the relationship between gamma and deep, middle, and superficial bolts that is preferential for presented versus non-presented stimuli. Now for the alpha results, and the results are slightly stronger here, but also a bit more complicated. So on the left, we have again the relationship for the presented stimulus. And this is a not presented stimulus. And in both cases, we find a negative correlation. But if you look closely, you can already see that the peak at which it peaks is slightly different. So for the presented stimulus, there's a peak around 10 to 14 hertz, roughly, where the negative correlation is strongest. For the not presented bolt signal, the relationship with alpha is actually in the lower alpha range. And this actually comes back to work from Klimesh already in the 90s, and it's stuff that I always try to ignore, but it somehow always bites me back whenever I do analysis, in where he basically separated upper alpha and lower alpha bands and related them to different cognitive functions. And it seems to come up here again as well. If we do look at the difference, we find that the difference is mainly, again, for presented versus non-presented in the upper alpha band, so 10 to 14 hertz. Again, for all three this time, I looked at the response for layers, and it's basically opposite of what we find for gamma, in the sense that the strongest relationship, which is in this case negative, we find for the deep layers, which is in line with what you would expect based on feedback related relationships for alpha. And it goes down when we go to more superficial layers, and it goes basically for all the results that we have here, and is strongest for the contrasts. So we find a different laminar profile here for gamma as we find for alpha. And it seems to be both cases related to feature-specific processes. But the complicating factor is that presented and not presented have a different exact frequency range within the alpha band. That seems to be related to lower alpha and upper alpha. And in the past, I've been actually looking into that as well. I stumbled into it. And we were also able to show that different cortical control networks relate differentially to upper and lower alpha, in the sense that the dorsal attention network seems to be more related to lower band alpha effects. At least this is in a resting state study. Well, upper alpha, more like 10 to 12 or 9 to 12 hertz, seem to be more related to what we called there, this is a mistake, the tonic alertness system. So a system that's related to being alert to novel stimuli. So this might be a handle on this to see, okay, maybe these frequency differences in the alpha response are related to different cortical control networks that have feedback projections. So in conclusion, this is just a summary of what I just tried to tell you. So what I've shown here is alpha, beta, and gamma have laminar specific correlates with bolts. Alpha, we found both deep and superficial correlates in the first experiment that I showed you. While beta, until now, we've only found a relationship with deep layers. While gamma is mainly middle to superficial, especially for V2, V3. Alpha and gamma correlate with feature and laminar specific bolts in V1. So the results that I've shown you now were only V1. Alpha shows the strongest relationship in deep layers. And it's frequency specific. The effect here is frequency specific. But the upper alpha band seems to be more related to feature-specific processes, and the lower alpha band more to non-feature specific processes. For gamma, the effect is weaker, but we do find a strongest effect of feature-specific bolt relationship with gamma in superficial layers compared to deep layers. So that was it, and thank you for your attention.
Yes, thanks very much. Do we have any questions for Rene?
Thank you, Rene. Very interesting work. So I had a question about the last study you presented. So there you focus on this kind of early increase in gamma band power, for example, which, if my memory serves me right, that is like typically quite broadband and sort of very related also to what you would see in the evoked potential, rather compared to the later part, which is typically a bit more sort of narrow band gamma band activity. So I was curious whether we could understand the correlation you show there as that when there is basically a general increase in the evoked potential, that is basically correlated with bold activity in a way that you generally also see with gradient echo bold, that you basically get an increase in the entire cortical column, which you then see the strongest in the superficial layers. Is that a correct way of interpreting it, do you think?
I'm not sure. Like the effects that we find now are, if you look at the spectrum, are quite narrow in our relationship with bold. So it seems that in the EEG that we measure, it's the narrow bold that's dominant. And I question how much of the broad bolds we can, broadband EEG, so the narrow EEG is dominant, but I don't know how much of the broadband electrophysiological response we can actually capture in EEG and properly distinguish that from all kinds of other broadband noise like the EMG. So it seems like the relationship here, I would say, are probably mostly narrow bands, although in the previous experiments, I've sometimes seen hints of broadband relationships between gamma and bolts, but I think that I would have to bet this would mostly be narrow band, I think. But the question is how much of a different process they represent. I think I've heard a talk from Andre Bastos at some point, who's saying that basically they seem to reflect at least the processes in the same layers. And whether or not one is a special case of the other, I don't know. But yeah.
Yeah. Okay. Thanks very much. Yeah.